In this lecture, we will discuss change of variable in multiple integral. So topic is change of variable. So sometimes we are not able to solve the integral directly or can solve easily. So we use the change of a variable. So we write down as sometimes we are not able to solve integration directly. So that can be solved by using change of variable. So we define let the integral double integral area under the region A f of xy dx dy. So we use the first method. So first method we take as the some relation is given. So first method let the relation x and y, relation of x and y are given as x is equal to function of ub and y is equal to function of ub. So then we convert the double integral as, so we write down the double integral over the region A function of fxy dx into dy is equal to double integral over the region we denoted as R, and the function we write down as f of x. X means function of ub, y function of ub, and dx dy we convert dx dy as Jacobian of du into dv. Jacobian of du into dv. So what is the meaning of Jacobian here? So Jacobian, because x and y are the function of u and v. So Jacobian J represent here del xy upon del ub. So this can be written as del x upon del u, del x upon del v, del y upon del u, del y upon del v. So this is the first form, or this form we will use as one variable. That means x and y convert into the another variable u and v by using some relation. Okay, so we remember that by using some relation, the variable x and y we can convert into the u and v. So that means it is not possible to solve directly in the form of xy. So we can use the another variable, that means relation we will use. Now the second form basically we use for the polar coordinate. So that means in coordinate system, first we have written as for Cartesian form. Now how to convert into the polar form? So for polar form we convert as put x is equal to r cos theta. So you know that the coordinate of a polar is r and theta, and we use the substitution here. r sine theta. Basically, you can say that x is the function of, we write down x is the function of r and theta, or here y is the function of r and theta. So basically, we use above form. Actually, that means we are converting xy into the form of r theta. So we write down as double integral a function of xy into dx dy. So this can be written as region D of f. X we put as r cos theta, y we put as r sin theta, and dx dy again we write down as Jacobian of dr into d theta. So what is the Jacobian here? So we again see the Jacobian. So basically the Jacobian J is equal to, we write down as x, y, and r theta. Xy with r theta. So you can evaluate this one. So del x upon del r, del x upon del theta, del y upon del r, and del y upon del theta. So this is equal to del x upon del r. When we differentiate x with respect to r, so gives us cos theta. Del x upon del theta, we write down as minus r sin theta. Del y upon del r, we write down as sin theta. And del y upon del theta, we write down as r cos theta. So what is the value of this determinant? So the value of this determinant you can write down as r cos square theta, or minus minus plus r sin square theta. So gives us r. So you write down as, so this value, that means this over the region D. So we write down as f r cos theta, r sin theta, or r dr into d theta. So you remember this one. So when we convert into polar form, that means changing the variable xy into the form of r theta, we use this. So we put x equal to r cos theta, y equal to r sin theta. Now third form we use for spherical polar form. So third form we use for spherical coordinates, spherical polar coordinates. For spherical polar coordinates, so we, you know that the spherical polar coordinates are r, theta, and phi. So here we use the substitution, or we can write down, we put x is equal to r sin theta into cos phi, y is equal to r sin theta into sin phi, and z is equal to r cos theta. So these are the spherical polar coordinate when we convert from Cartesian to polar. So now we use for triple integration. We are for using for triple integration. That means x, y, z, dx or dy into dz. So this equal to, we write down the triple integration of f, r, theta, and phi, and gives us Jacobian of dr, d theta, and d phi. So here the Jacobian we use as x, y, z upon r, theta, and phi. So you can calculate this, and we write down directly the value of this is r square sin theta. We have already discussed this into Jacobian portion. So you can write down this as f of r, theta, and phi into r square sin theta, dr, d theta, and d phi. So basically we use this formula for in the change of variable. So basically for double integral we use above two, and for triple integral case we use third one. So we start the problems. The first problem we take for polar. So that means evaluate the integral. Evaluate the integral 0 to a, 0 to root a square minus y square, x square plus y square, dx into dy by changing into polar coordinates. By changing into polar coordinates. So here we are changing this into the polar coordinates. Okay, so this is the given form is the Cartesian form. Now we want to change into the polar form. So the limits are, we write down that the given limits are, so first limit is purely constant limit, second limit is your variable limit, the variable limit in terms of y, so obviously these limit for x. So this limit for y and this limit for x. So that means y equal to 0 and y equal to a. And second limit x is equal to 0 and x is equal to root a square minus y square. So now we focus on this particular limit. So that means we see that when we do the square of both sides, so this gives us x square equal to a square minus y square. So we can write down this as x square plus y square equal to a square. So that means this represent the circle. So this represent the circle whose center is origin. So we write down as represent the circle whose center is origin and radius is a. And radius a. So now when we are talking about as per limit, so that means we trace a circle, we draw a circle. So that means this is our x-axis, we considering it, this is our y-axis, here is the origin. Now we are talking about only first quadrant. We are talking about only first quadrant because the limits, initial limit means lower limits are given from 0 to a or 0 to root a square minus y square. So you know that when along x-axis, means y is equal to 0 or along y-axis x is equal to 0. So we are talking about the first quadrant only. So this is our first quadrant. So only for this quadrant, we are going to evaluate the integral. So here, now we see that when our limits, variable limits for x. So these this means that our elementary strip is parallel to x-axis. When our limits variable limit for x, so we take the elementary strip parallel to x-axis. Now, what is the boundary for this? So the boundary of this is equal to x is equal to root a square minus y square because this represents the circle. So circle in the first quadrant. So here we have the limit x is equal to 0. So this boundary gives us x equal to 0 and this boundary gives us x equal to root a square minus y square because this represents a circle. So x square plus y square equal to a square. So here we have a y equal to 0. So y equal to 0 and the ordinate, this ordinate will, so this ordinate will be the 0 comma a. So this ordinate will be the 0 comma a. So now this is for Cartesian form. So this is for xy plane Cartesian form. Okay. So now when we talk about the polar coordinates or polar form, so we see that we have an initial line. So for initial line, so this x-axis we treat as initial line. For this line, we take as theta is equal to 0. For this line, theta equal to 0. Initial line here is theta equal to 0. So when we are talking about only first quadrant, means this quadrant from this to this. So now at this level, so that means theta will be the pi by 2, 90 degree. So theta will be the pi by 2, 90 degree. When we take the elementary strip, which does this boundary, and we make the angle theta. So you know that when we convert dx dy into the form of polar. So this can be written into the form r d theta dr. So now what is the limit for r? So what is the limit for r? So when we take the element is which touch the curve, which touch the curve. So here at origin, the value of r should be 0, means radius will be 0. Or when we touch this curve, so we can calculate as. So when this touch the circle. So that means we put the polar coordinate x equal to r cos theta. So we write down as r cos theta to the square or y equal to r sin theta. So r sin theta to the square is equal to a square. So this gives us r square is equal to a square. So this gives us r equal to plus minus a. So plus minus a radius will be positive. So we consider as r equal to a. So you can clearly understand that the limit. So here we write down the limit of r. The limit of r is r equal to 0 to r is equal to a. And limit of theta, so we write down the limit of theta because we are talking about only first quadrant. So first quadrant initial line theta equal to 0 to theta is equal to pi by 2. So here both limits are constant. So both limits are constant. Now we convert that this integral. So this above integral into the form of the polar. So we write down first y equal to 0 to a, or x is equal to 0 to root a square minus y square into x square plus y square. So into x square plus y square dx into dy. This can be converted into the form of r. Limit of r is equal to 0 to a, limit of theta is equal to 0 to pi by 2. Here both limits are constant. Now we put the value of x square plus y square. So what is the value of x square plus y square? Obviously the r square. So x square plus y square equal to r square. So into dx dy. So dx dy is obviously r d theta into dr. Okay, or you can say that the Jacobian of dr into d theta. So Jacobian of this is equal to r. So we directly write down as r d theta dr. So now when both limits are constant, we can integrate any one of them first. So first we integrate with respect to r. Okay, so we take a theta limits as 0 to pi by 2 when we integrate with respect to r. So here is r square into r means r cube. So what is the integration of r cube? The integration of r cube is r4 upon 4. And limit is 0 to a, or here we write down as d theta. So this can be written as theta equal to 0 to pi by 2. This gives us a4 upon 4 into d theta. So a4 upon 4 is purely constant. We take outside from the integral. So we write down as a4 upon 4 and can be written as theta equal to 0 to pi by 2 into d theta. So this gives us a4 upon 4. And what is the integral of d theta is theta. So we write down as pi by 2. So this can be written as a4 upon 4 into pi by 2 minus 0. Okay, so what is the answer of this? So answer of this is pi a4 upon 8. Pi a4 upon 8. So this is our answer. Okay, so hope you understand how to find the limits in the form of polar and how to evaluate this. So integral is given into the form of Cartesian and we convert it into the polar form, and also we change the limit. We take the limit as for polar form and we integrate this one. Okay, so this is the first formula, that means we have changed of variable from Cartesian to polar. Now, we have another type of problem, that means when relations are given, so how to solve that type of questions. So we take a second type of questions. So now question is given using x plus y equal to u, x minus y is equal to b. So then evaluate the double integral over the region R, x square plus y square into dx dy. The integration being taken over the area bounded by the lines x plus y is equal to 2, x plus y is equal to 0, x minus y is equal to 2, x minus y is equal to 0. So here we convert this xy means Cartesian form into the another form that is called UV form. Okay, so the relation is given. So these relations are given. So when we are going to solve this, this is for xy. Now we converted this into the form of UV. So when we are going to convert this into UV, so we need x is the function of UV. We write down as we require x should be the function of UV and y should be the function of UV. So we use these given relations, and we make x is the function of UV and y is the function of UV. So here we write down as given that x plus y is equal to u. So this is our equation number 1. X minus y is equal to v. This is our equation number 2. So now we adding these two. So when we add these two, y to y cancels. This gives us 2x. 2x is equal to u plus v. So x gives us u plus v upon 2. So x gives us u plus v upon 2. So this is our equation number 3. So we got the first uh, relation for x in terms of uv. So here we have x is the function of uv. X is the function of uv. Now we solve for y. So when we solve for y, so putting this value of x in equation 1, so put in 1. So when we put in 1, so we write down as u plus v upon 2 plus y is equal to u. So this can be written as y equal to u minus u plus v upon 2. So this gives us 2u minus u plus v upon 2 gives us u minus v upon 2. So u minus v upon 2. So you can write down this as y equal to u minus v upon 2. So this is our equation number 4. So obviously we see that so y is also the function of uv. So y is also the function of uv. Now after making x and y function of uv, we obtain the Jacobian. So we required the change. That means first we obtain Jacobian. So when we obtain the Jacobian, so Jacobian of xy with respect to uv. So Jacobian of xy with respect to uv. So we write down as del x upon del u, del x upon del v, del y upon del u, and del y upon del v. So this gives us del x upon del u. X with respect to u gives us 1 by 2. Del x upon del v gives us 1 by 2. Del y upon del u gives us 1 by 2. And del y upon del v gives us minus 1 by 2. When we solve this determinant, this gives us minus 1 by 4 into minus 1 by 4. So minus 1 by 4 or minus 1 by 4 gives us minus 2 by 4. So means minus 1 by 2. So the value of the Jacobian is minus 1 by 2. Now, after evaluating Jacobian, we move to the question. So that means first here we draw xy plane. So we draw xy plane. So this is our x-axis. Here is origin. This is our y-axis. And this is we can consider x dash, or here we consider as y dash. Okay, negative. So we take a scale. That means we consider this is our 1, 2. Here we have taken 1 and 2. Here we take as minus 1. So minus 1 or minus 2. also -1 and -2. Now, first line area, that means region bounded by the line. So first line is x plus y equal to 2. So first we draw the x plus y equal to 2. So x plus y equal to 2. So drawing this line, so you know that when we draw first line x plus y equal to 2, so here we do the some rough work, or you can say that. So x plus y is equal to 2. So how to calculate the coordinates? So just we put y is equal to 0. So y equal to 0 gives us x equal to 2, or x equal to 0 gives us y equal to 2. So 2 comma 2. So that means 2 comma 2. So here x equal to 2, y equal to 2. So these are the coordinates. So we draw the line intersect this one. So this is line represent the x plus y is equal to 2. Now for second line, x plus y is equal to 0. So means x is equal to minus y. So x equal to minus y. So this gives us here. So x equal to minus y. So this is our x equal to minus y. Okay. And now this is x plus y equal to 0. Third line is x minus y equal to 2. Third line is x minus y is equal to 2. So means put x equal to 0, y equal to minus 2, or y equal to 0, x equal to 2. So that means uh, y equal to minus 2. So y equal to minus 2 is here, and y equal to minus 2 or x equal to plus 2 is here. So we join this one. Oh, sorry. We join this. So so this is our third line. This represents the x minus y equal to 2. Now fourth line given as x minus y equal to 0, means y equal to x or x equal to y. So y equal to x means this is our fourth line. So y equal to x, this is our fourth line. So x equal to y or y equal to x, you can. So what is the bounded region? So this is the bounded region. So this is the bounded region as per the given question. So this is our bounded region when we are going to evaluate this integral. So this is our bounded region. Okay. Now, but we are not solving this for Cartesian form. We are solving for UV form. So you can write down this is our XY plane. So this is our XY plane. And now we are solving for UV plane. So we draw UV plane. So this is our U and this is the V. Okay. So UV plane. So we see that the relation given as x plus y equal to U, and line is given as x plus y equal to 2. So that means we directly write as u equal to 2. So given as x plus y is equal to 2. Okay. And line is x plus y is equal to 2. So directly we write as u equal to 2. Second line, x plus y is equal to 0. So x plus y equal to 0 means we put u equal to 0. So this is for u, and the second given as x minus y equal to v. So second given as x minus y is equal to v. A line given as x minus y is equal to 2, so gives us v equal to 2. And second line given as x minus y equal to 0, so v equal to 0. So it is clear. Here is the origin. So along that means u. So v equal to 0, v u equal to 0. Okay. Now we take here is 1 and here is 2, 1 and 2. So u equal to 2. When we draw u equal to 2, so this gives us parallel to v, and v equal to 2 parallel to u. So this is our bounded region. That means we are solving for this one. Okay. So make a square. So this is our bounded region. So we are going to evaluate the integral for this. Okay. So directly you can see that what is the limit. So limit from u equal to 0. So we write down the limits are u equal to 0 to u equal to 2 and v is equal to 0 to v is equal to 2. So after obtaining the limits, we evaluate the integral. So when we evaluate the integral, so integral is given as integral over the region R x square plus y square into dx dy. This can be written as double integration with the limit of ub. So u is equal to 0 to 2, v is equal to 0 to 2, x square plus y square. So what is the value of x? The value of x we have u plus v upon 2. Calculated v plus u plus v upon 2. So we write down u plus v upon 2 to the whole square and u minus v upon 2 to the whole square. And to dx dy, so we convert Jacobian of du into dv. So you simplify this. So u is equal to 0 to 2 and v is equal to 0 to 2. And when we solve this, so directly 4 will take in common. So gives us u square plus v square plus 2uv plus u square plus v square minus 2uv. So 2uv to 2uv cancelled. Jacobian value is minus 1 by 2 and du into dv. Now we write down this as u equal to 0 to 2, v equal to 0 to 2. So this gives us 2u square plus v square upon 4 or into minus 1 by 2 into du dv. So 2 to 2 cancelled. Minus 1 by 4 taken outside the integral gives us u equal to 0 to 2, v equal to 0 to 2, u square plus v square into du dv. Okay, so both limits are constants. We can integrate any one of them first. So first we integrate with respect to v. So we take as u equal to 0 to 2. So when we integrate with respect to v, so this gives us u square into dv. U square into dv, so means u square and dv integration is v plus v square means vq upon 3 and limits are 0 to 2 into d. So this gives us minus 1 upon 4 integral u is equal to 0 to 2. And when we put the limits, so this gives us 2u square plus 2 to the 4 to the 8, 8 upon 3. Or when lower limits gives us 0 into du. So this equal to minus 1 by 4. And we write down this as u is equal to 0 to 2, 2u square plus 8 upon 3 into du. Now we integrate this with respect to u. So this can be written as 1 by 4. So 2 u cube upon 3, u cube upon 3 plus 8 upon 3 into u or 0 to 2. So when we apply the limits, so 2 to the 4 to the 8, 8 to the 16, 16 upon 3 plus or 2 8 the 16, 16 upon 3 uh, minus lower limit, so both are 0. So 16 plus 16, so minus 1 by 4 into 32 upon 3. So 32 upon 3, so a 4 8 is a 32. So this gives us minus 8 upon 3. So this gives us minus 8 upon 3. So this is our answer. So minus 8 upon 3. Okay. So now we take a one more problem related to that. So next problem is using the transformation using the transformation x plus y is equal to u and y is equal to uv, show that integral 0 to 1, integral 0 to 1 minus x e raised to the power y upon x plus y into dx dy is equal to 1 upon 2 e minus 1. Okay, so when we solve this question, so same transformation is given as x plus y is equal to u and y equal to uv. So first we write down in the form of x equal to function of uv or y equal to function of uv. So how to write down this? So we write down the x plus, we write down this value of y, so y gives us uv is equal to u. So x gives us u minus uv. So this can be written as u into 1 minus b. So here we write down x equal to u into 1 minus b. So u is the function, x is the function of uv. Okay, so this is our first equation. So x is the function of uv, or for y is obviously given in the form of uv. So this is given into the form of uv. So we use these two. Okay, so when we use these two, so now we obtain the Jacobian. So when we obtain the Jacobian, so Jacobian of what? Jacobian of xy upon Jacobian of uv. So this gives us del x upon del u, del x upon del v, del y upon del u, del y upon del v. So this gives us del x upon del u. So del x upon del v means 1 minus b, del x upon del v means minus u, del y upon del u, v, del y upon del v, u. So this we can write down the u minus uv, or this gives us minus minus plus uv, uv to uv cancelled gives us u. So the Jacobian value, the value of the Jacobian gives us u. Now we see the limits. So when we see the limits, so limits of the integral is given as 0 to 1. So first the variable limit is second. So this variable limit is for y and this limit purely for x. That may be because this is constant limit. Now, so we see that the given limits are x equal to 0 to x is equal to 1, y is equal to 0 to y is equal to 1 minus x. Okay, so we focus on this particular limit. So when we focus on this particular limit, so you can write down this as x plus y is equal to 1. So we can write down this as x plus y equal to 1. So when you draw the Cartesian plane, that means this is our x-axis origin and y-axis. So now we see that so this is our x-axis origin, y-axis. We see that x equal to 0. X equal to 0 means y-axis. X equal to 0, y-axis. Y equal to 0 is x-axis. X equal to 1. So x equal to 1. So here we take 1. So we draw x equal to 1. And x plus y equal to 1. So x plus y equal to 1. So when x equal to 0, y equal to 1, y equal to 0, x equal to 1. So this is the line. Okay. So this is the line. And we are talking about this region, shaded region. This is the triangle shape. So we are talking about this region. This is our bounded region. And what about the elementary strip? So the elementary strip, the limit is variable for y. So the elementary strip obviously is parallel to y-axis. So y-axis here we represent it as y equal to 1 minus x. So elementary strip is for parallel to y-axis. So this is the xy plane. So hope you understand as per the given limits xy plane. Now we need to convert, draw the UV plane. So when we convert UV plane, so UV plane we take help of the given relation. So given relation means x plus y equal to v. So we use x plus y equal to u and y equal to uv. So x plus y equal to u and y equal to uv. Okay. So first we write down as from 1 and 2. From 1 and 2, x gives us u into 1 minus v. From 1 and 2, so we are taking as first one. So in this we put, this is our lower limit for x. So put x is equal to 0. So when we put x equal to 0, so 0 is equal to u into 1 minus v. So 0 into 1 minus v, it gives us u is equal to 0 or v equal to 1. So 1 minus v equal to 0 gives us v equal to 1. So these are the limits when we put x equal to 0. So when we talk about the y equal to 0, so y equal to 0. So when we put y equal to 0, so this gives us u into v is equal to 0. So gives us u equal to 0 or v equal to 0. U equal to 0 or v equal to 0. Third one, we put x plus y is equal to 1. So here we have x plus y equal to u. So directly we can write down a u equal to 1. So u equal to 1. So the limits are clear. So that means the limits of u, the limits of u is from 0 to 1 and limits of v is also from 0 to 1. So when we draw the UV plane, so this is our u, this is v, and when we put u equal to 0, so here is u equal to 0, here is v equal to 0, and we take as 1, u equal to 1, v equal to 1, v equal to 1. So this is our shaded portion. So we are going to evaluate for this portion. Okay, so here both limits are constant. So just we evaluate for this. So this is our shaded portion. Now we solve the integral. So integral is given as 0 to 1, 0 to 1 minus x. Now integral given as 0 to 1, 0 to 1 minus x, e raised to the power y upon x plus y upon x plus y, dx into dy. So this can be written as the both limits for u and v are 0 to 1. So convert it into 0 to 1, 0 to 1, e raised to the power y. So what is the value of y? Y value is ub. And what is the value of x plus y? So x plus y is u. So x plus y is u into dx dy. So dx dy means Jacobian of du into dv. So this can be written as u is equal to 0 to 1, v is equal to 0 to 1. So e raised to the power v and Jacobian is u and du dv. So Jacobian we have already solved. So this gives us u. Now we just solve this integral. Both limits are constant. We can integrate any one of them first. So first we integrate with respect to v. So we take as u equal to 0 to 1. So we write down u into integration of e raised to the power v is e raised to the power v 0 to 1 and du. So this equal to 0 to 1 u and e raised to the power 1 minus e raised to the power 0 into du, upper limit minus lower limit. So u is equal to 0 to 1 u. So e minus e raised to the power 0 is 1. So du. So e minus 1 is purely constant. So we take outside from the integral and we have u is equal to 0 to 1 u into du. So we integrate this. So e minus 1 integration of this is u square upon 2, 0 to 1. So this equal to e minus 1. So we write down as 1 upon 2 minus 0. So this gives us 1 by 2 into e minus 1. So this can be written as 1 by 2 into e minus 1. So this is our answer, or we can say that we have proved